This is the inflation tutorial I promised, and I'm just going to start by saying inflation is one thing. So inflation is different things. It's a concrete technical idea with a great phenomenology, and I'm going to tell you about that. I'm not going to assume you know much and about it. But it's also couched in the language of solving tuning problems. And it has big open questions, which are very closely related to this, and actually related to the other thing as well. And I'm going to pop right to the conclusions. There's more to the talk, but here are the conclusions.
I just thought I'd fallen asleep.
Yeah. Oh, I'm glad. I don't think I have, but.
Wait, just take questions?
Yeah. Yeah. That's. Yeah. So any questions? Inflation is a technical tool for connecting cosmological observables with high-energy physics, and in that role, it's had impressive successes. However, without a meta-theory, and by meta-theory I don't mean do you believe in God or something like that. I mean just a completion of a technical completion of various aspects. It's hard to tell how it fares compared with other scenarios, and how to resolve some big questions that are unresolved. And given the situation, we encounter really complex sociology as different individuals choose to emphasize, to give different weights to A and B. And so a lot relies on priors. We've had conversations already this week about what science is like when a lot depends on people's priors. And it usually means that science hasn't gotten very far yet. And so people work, between gathering more data and between, the process of people's priors shifting, you hope to arrive at a point where, the really solid results in science aren't dependent on people's priors. And when a lot does depend on priors, I think very intrinsically it's dissatisfying in science. It's a dissatisfying feeling, and it's often complicated and fraught, and even in principle. And I would say in practice we've been really true to that, and it has been complicated and fraught in practice as well as in principle. Yeah.
So there is an in-principle limitation as a cosmologist versus a particle physicist in that you can't get to repeat the experiment numerous times and do frequentist analysis if you wanted to, but you're just intrinsically limited by the fact that for some things you have to do Bayesian inference.
So I am talking about Bayesian, and right. So I think this grand statement I don't think is that. I don't think it should be phrased that way. I said this once while having lunch with Tom Kibble, and he totally pushed back very hard in a way I respect a lot, which he said, look, every field of science has its limitations. You only have a finite set of data. You only, it hopefully grows, and it certainly has been growing massively in cosmology. But the finiteness of the data places limitations on what you can say. And you just do your best within those boundaries, and there's limits to what we can say in particle physics. And yes, there's different. The thing you can control by building a new accelerator in particle physics is different. But what you can do in cosmology is take more data and come up with clever ideas. There's really interesting ideas about how to do more subtle things with what's out there. So they're different, but each is bounded, and each, it's an uncertain thing. How much further we can go with sheer cleverness and technology and all of that. So I don't put those on such separate footings, but I think every field has to face those real limitations. Every field has practical limitations, and we have to confront them. Was that Charlie?
Yeah, well, in social sciences, there are all sorts of things that you can't really settle by feasible experiments. And so there's a lot of sociology
in sociology as well. Yes, indeed. And actually, there's this inherently unsatisfying feeling of duking it out in the world of priors, And I realized, so when I was being asked to give this tutorial, and I sort of said, well, why don't we do maybe someone younger do it, maybe without them. Part of it is this discontent. I mean, I've been duking it out with the senior figures in inflation theory my whole career in terms of these priors, and it's not
like most of the career of inflation, right?
Yeah, right. So I count myself as one of the old farts of inflation, and we have been droning on. We've been posturing about these priors the whole time, and I think, you know, what nature has to say about that situation, what nature offers as a resolution of that situation, is the next generation, right? So of course I'm ambitious and I want to solve it all before I'm done, but I think it's very healthy that young people bring their own perspective to all these debates, and I appreciate that Henry said some good things in this talk, and I asked, so in the end what I negotiated with Adam is that I'll give the talk, but he has to be in the audience, which he's not, and call me on my bullshit. I don't know if he decided there was too much bullshit to. You better get okay. So quick, get the bullshit out. But it was interesting. So, and I really am weary of all this debate, ponderous debate about priors. And I went through, it was kind of, last night as I was putting this together, of course I have slides, it's not like I had to write new slides, but I tried to exercise the debates of priors out a little bit so I could give you the nuggets of technical stuff and separate it. And then I found myself at the end, so you know when you write a PowerPoint slide and the text box, all of a sudden you realize the text box has gone way below. You're typing line after line and the text box goes way below the slide. So I was in that position.
Down where the extra.
Yeah, right. It would have gone right buried in the blackboard. Sorry. So I just deleted it all and kept it really simple, and then even moved it to the front because that is where I am with this now. Is I'm sick and tired of all the debates about priors, although that is where we are. So I want to say things in a more concise way, but I promise you I will tell you my priors at the end. But I want to keep it kind of open, and probably the most important thing, well, I think the most important thing would be is if we had some technical results that helped us go past this debate about priors.
So it actually gets a little bit more annoying than, as you elucidated there, because sometimes there's like the pretense of a debate that happens where people actually go meta priors to try and justify why B isn't a problem, for example.
Oh, exactly. No, I've been right. So I've gone from this, like a couple days ago, grousing with Adam about the old farts pontificating, and I'm trying to mellow myself out so I'm not so negative. I don't like spending my time being negative, but yeah, it gets really terrible, and yeah, especially when people are trying to protect themselves from B by pretending it's all, yeah. So yeah, I I've seen all that. Yeah, right.
There is really no hope to draw some kind of practically testable consequences that could be.
There are practically there are. But it's an incomplete thing, and so I will. So that's where there absolutely are practically testable things, and I've added, some of my current work is adding a few more, but it's incomplete, and.
Well, if your prior is that you totally believe in one thing and not in another thing, then
You're set.
Doesn't help.
Yeah, exactly. Yeah, right. Yeah, exactly. So we're in this situation. So now I just want to launch in, and I want to actually. I have one more reflection, very appropriate for this location. So one of the things that has fascinated me throughout my career is how confused the physics community is about quantum physics, and we love to see ourselves as these hard-nosed practical characters who just get on with it, take the data, solve the equations, and get on with it. And here we go on and on about the different interpretations of quantum physics and all, as we all know. And I've started. This is, when I was in high school, excited about physics, and then I read the chapter at the end of the book about quantum physics. it just blew my mind that people were sort of forced into rethinking how they saw the world. And so it's a beautiful thing, but also really strange how confused we are. It's strange, given our supposed nature of being so practical. But I've recently sort of shifted a view a little bit on that, saying, well, the great thing is that we've discovered quantum physics, that we were capable of discovering such an amazing thing. And it's not at all surprising that we get totally confused about it. Not just the physics community, but then hippies think it has to do with Eastern thought, and this whole thing. I think that's just like, what do you expect from humanity? We're these passionate, complicated creatures, and what a wonderful thing that we discover. That we've discovered quantum physics and are trying to deal with it. And you could say some of the same things about inflation. I mean, what a thing to actually have a theory about the initial state of the universe. It's like, wow, who would have thought we could even try that? And you can get bogged down in B and wonder how much we've succeeded in that. But I think there's no question that we've tried it and we've turned it into something that can. There's a procedure for relating that theory to tons and tons of data, and that's a pretty amazing thing. And maybe we shouldn't be surprised if we're also very confused about exactly where we are with that, because it's a really huge thing, and it's just been around a few decades. So I think. So I'm feeling more okay about it. So we're it's annoying to wallow in priors, but come on, we're being very ambitious, and it's exciting. So I'm going to carry on now. So I'm going to try to really be clear about when I'm just giving you technical stuff, although the priors will come in. So I'll start with the technical and then embrace more of these topics. So here's the outline. So let's start with the Big Bang. Forget about inflation. Tell you a few things about the Big Bang. I'm not going to assume everyone knows this. So you take Einstein's equation, and what have I done? And you impose symmetries, and the history of these symmetries is interesting. I'm not going to dwell on it in the talk, but we can reflect on that together if you want. It started with principles rather than observations, and now we have so many observations we can sort of turn that around to some degree. But anyway, you take these complicated equations and impose a symmetry and get this amazingly simple equation where the one dynamical degree of freedom is just a scale factor, and in the metric, the one dynamical degree of freedom is the scale factor, and you have this equation. The scale factor is, as Henry said the other day, it just sort of measures the overall expansion of the universe. And then you can relate the expansion rate to the matter in the universe. And there's all these...
Those different rows, yeah.
And so I'm going to tell you about this. So this is the Hubble parameter. We often know it as the Hubble constant because today it takes billions of years to change much. So it seems like a constant, but actually it's a highly evolving thing in the big picture. And there's a scale factor I already talked about. This is a little bit of a cheat. So these rows are all energy densities. This is really part of the metric, the curvature, but you can always shift things to. So I re-express it as a density to so you can see a little more clearly how it relates to other parts of the equation. It's just a reworking. You basically bring out this factor of g, and then it looks like a density, and here it is more comparable to these other things. There's some relativistic matter, rho r. There's non-relativistic matter, which people insist on calling matter. And then there's the dark energy. So there's all these things, and each of these has its own way of scaling with the scale factor as the universe evolves. And so you can plot this on a log-log plot. You have these different components. You see how they evolve, and from that you get a picture of the universe that has incredibly wonderful things in it. First of all, the temperature, so here we are today, very low temperatures, but due to the expansion of the universe, the temperature's been cooling, and so you get a model where the temperature is very high in the past. And one of the benefits of this high temperature is that you're exploring different energy levels of physics. So whereas humans struggle to invest billions of dollars to make particle accelerators to inch the energy level up a little bit, for the universe, high energy collisions are once totally common, totally boring everyday things, much higher energies than we achieve in the accelerators so far. So you can apply the different, so there's different things that happen at different stages. Lots of data, at this point, lots of data people take. For example, one of the things that happens in this history of the universe is that at very high densities in the past, the universe was opaque. Photons couldn't go very far at all without hitting something else. And then there's this moment, there's this period where the universe transitions into transparency, and then you can, this is called the surface of last scattering, and you can, because you're looking back in space, you're also looking back in time, because stuff takes time to get to you, you can actually look